day, everyone. Now, our group will be discussing about the graphical methods for mirrors with spherical mirrors. Now, for the learning objectives of our lesson, first, differentiate between concave and convex mirrors based on their structure and image formation. Second, illustrate the graphical or ray diagram method and apply the mirror equation to determine image distance and characteristics. And lastly, explain the applications of spherical mirrors in real life situations. Okay, so what are spherical mirrors? So a spherical mirror is part of a sphere surface that reflects light. Now, spherical mirrors have two types. First, the concave mirror or converging. So when we say concave mirror, let's just remember the word converging. So it curves inward and can form real or virtual images. Now, the next type is the convex mirror. So when we say convex mirror, it's diverging. So let's remember the word diverging. So it curves outward and it always forms virtual, upright, and diminished images. So spherical mirrors are used to form images based on the laws of reflections. As we what we can see on the image, so we can see what's the difference. What are the differences between the concave mirror and convex mirror? Now here are the key terms. First, center of curvature. So it is the center of the sphere from which the mirror is cut. Also, the radius of curvature is the distance between the pole and the center of curvature. Next, a principal axis, a straight line passing through the pole and center of curvature. Next, aperture. It is the portion of the mirror surface that reflects light. And there is also focus, point where parallel rays converge or concave or appear to diverge or convex. And lastly, a focal length. So focal length is the distance between the pole and focus. So there's an equation. I think this is an equation that F is equals to R over 2.
Good day, everyone. So, this slide shows the graphical or the ray diagram method, which is a visual way to locate the image formed by spherical mirrors. So, as seen in the figure, part A shows the concave mirror and part B shows the convex mirror. So, for the concave mirror, the image formed can be real or virtual depending on the object's position. However, for the convex mirror, the image is always virtual, upright, and smaller than the object. So the image appears behind the mirror between the pole and the focus. Now, by drawing at least two rays using the ray tracing rules, we can determine where the image is located and what type it is. Let's talk about the rules of ray tracing, which helps us determine how light behaves when it reflects on spherical mirrors. So first, a ray parallel to the principal axis reflects through or from the focus. Second, a ray passing through the focus reflects parallel to the principal axis. And third, a ray through the center of curvature reflects back on itself. And lastly, a ray hitting the pole reflects symmetrically following the law of reflection. So, by using these rules to trace at least two rays, we can find where the image is located and identify if it is real or virtual, upright or inverted, and magnified or diminished. Finally, we have the slide about images formed by a convex mirror. So a convex mirror is curved outward and it is also called a diverging mirror because it spreads out the reflected rays. So no matter where the object is placed, a convex mirror always produces an image that is virtual, upright, and diminished, meaning it looks smaller than the object. So the image always appears behind the mirror, regardless of the object's position. So that is why convex mirrors are commonly used as vehicle side mirrors, as they give a wider field of view, allowing drivers to see more area behind them, though the image appears smaller.
As we can see in this slide, the concave mirror curves inward, like the inside of a spoon. The diagram shows that the image changes depending on where the object is placed. When the object is far from the mirror, the image appears smaller and inverted. When the object moves closer, the image becomes larger. But when it's between the focal point and the mirror, the image becomes upright and magnified. That's why concave mirrors are used in things like makeup mirrors or shaving mirrors because they make the face look bigger. So, basically, a concave mirror can form either a real or a virtual image depending on the position of the object. So next, uh, this shows the mirror equation. It's a simple formula that helps us find exactly where the image is formed. It's written as 1 over f equals 1 over object distance plus 1 over image distance. So here, f means focal length. Object distance is the distance of the object and image distance is the distance of the image. Even though we can see the image clearly through a ray diagram, this formula gives the exact measurement for where the image will appear. So the next the next slide is an example of using the formula. So it shows that if the focal length is positive 15 centimeters and the object distance is 10 centimeters, so the image distance comes out as negative 30 centimeters. That negative value means the image is virtual, upright, and magnified, which matches what we see in the diagram on the slide. So the formula and the diagram both prove how concave mirrors can produce larger and upright images when the object is close to the mirror.
Now proceed to the analytical method for comparison. Now, while ray diagrams gives us a visual idea of where an image will be, we can get exact results using the analytical method. So this method relies on one key formula only, which is the mirror equation. It is 1 over f equals 1 over do plus 1 over di, where f is the focal length, do is object distance, and di is the image distance. So let's apply this into two examples. We have first the concave mirror. We have the given our focal length is equal to positive 15 centimeter and the do is equal to positive 10 centimeter. So we want to find the image distance. So our formula for this is 1 over f equals 1 over do plus 1 over di. Since we want to find the di, let's rearrange first the formula. So 1 over di equals 1 over f minus 1 over do. So step 2, let's substitute the given values, which is 1 over 15 minus 1 over 10. So dili na to siya subtract first because we need to find first the common denominator sa 15 and 10, which is 30. So we have now the di equals 2 over 30 minus 3 over 30. Nganong na 2 naman ni og 3 diri, it's because kanang ang 15 is ma-times siya into 2 para makakuha tag 30. And also, ang 30, 3 ang dapat i-multiply sa iya to get the 30. So, let's multiply this side by side lang. 1 times 2 equals 2 over 15 times 2 equals 30 and 1 times 3 equals 3 over 10 times 3 equals 30. So, this gives us 1 over di equals negative 1 over 30. So, step 4 is i-reciprocate lang dahil nato siya para makuha nato ang image distance. So, mahimo na din siyang 30 over negative 1 is atong di is equals to negative 30 centimeter. So this result means the image is virtual tungod sa negative sign, right? And we can also check the magnification using the formula negative m equals negative di equals do. So substitute lang din nato ang values, which is negative and open parenthesis of negative 30 over 10, which is equals to positive 3. So the positive magnification means ang image is upright, and since 3 is greater than 1, the image is magnified. So kung magamit dito or mag-hold ta og makeup mirror, no, it's a concave mirror, kanang close to our eyes, we see a magnified, upright, and virtual nga image. So let's proceed now to the convex mirror. So we have the given our focal length is equal to negative 10 centimeter and our object distance is equal to positive 20 centimeter. So we use the same formula, the 1 over di equals 1 over f minus 1 over do. And substitute the given values, negative 1 over 10 minus 1 over 20. So let's find first the common denominator para masubtract sila, which is 20, right? 20 ang pwede ma-times ay ma-divide sa 10, and pwede po ma-divide sa 20. So, negative 2 over 20 minus 1 over 20. So, our image distance is equal to negative 3 over 20. And then, step 4, let's reciprocate to find our image distance. So, negative 20 over 3 is equal to, our image distance is equal to approximately negative 6.67 centimeter. So, it means that the image is virtual because of negative sign, and also it's upright and it's diminished. So let's always remember that in this case, no, for all convex mirrors, it always produce a virtual, upright, and diminished nga images. Its applications of spherical mirrors, no, it used in optical instruments, classroom demonstrations, and engineering designs. It also helps analyze the real and versus virtual nga images, and magnification and reflection also. It also used, no, sa kanang concave mirrors are used for magnification, focusing light, and its examples are kanang telescopes, microscopes, and makeup mirrors, car headlights, and flashlights. For convex mirrors, these are used for wider field of view. The best examples are the passenger side mirrors on cars, no, because the drivers can see much wider area, and it used for security mirrors in stores. And here's our references. Thank you.